innovative technology for excellent solutions. Customers worldwide trust Peerless to create high quality, reliable equipment, meet critical solutions, and sanitation requirements, provide attentive after-sales service to optimize processes and reduce downtime. The bread and roll, biscuit and cracker, and cake and snack market segments use Peerless equipment. I'd also like to introduce our speaker today for this webinar, Mr. John Cremines. John joined Peerless in December of 2003 as a controls engineer. He has over 16 years experience in industrial control systems such as PLCs, motion control, VFDs, HMIs, hydraulic and pneumatic design. He has a solid practical design concepts as well as excellent problem-solving skills. John holds a Bachelor's of Applied Science in Automated Manufacturing Technology as well as Associate of Applied Science in Electronics Engineering Technology from the ITT Technical Institute. Please welcome Mr. John Cremines.
Welcome to the second webinar by Peerless Food Equipment in 2013, a series to help our customers and partners become more efficient in their businesses. This particular topic today, advantages of VFDs and industrial equipment, will be educational and help better understand what VFDs can do for you and the life of your industrial equipment. We will discuss motor starters, VFDs, and the advantages and disadvantages of each. Thank you for taking the time to participate in the Peerless Food Equipment webinar, as we know your time is valuable and we hope that you find the time spent with us today informational and helpful. Here is a summary overview of what we will discuss today. First, we are going to explain what a VFD is and how it works. We will also look at energy savings and the benefits of using a VFD for your mixer drive. I will outline the advantages and disadvantages of two-speed starters and VFD systems as used in Peerless equipment today. VFDs and how they work. For more than 40 years, variable frequency drives, or VFDs, have been a critical component of commercial and industrial systems. Today, their fundamental usage has remained the same, while technology has evolved and improved, yielding drives that are better able to reduce energy consumption and improve reliability while extending equipment life. A VFD is an electronic controller that adjusts the speed of an electric motor by regulating the power being delivered. VFDs provide continuous control, matching motor speed to specific demands of work being performed. They are an excellent choice for adjustable speed drives users because they allow operators to fine-tune the process while reducing costs for energy and equipment maintenance. In other words, they help you use the energy you need and no more. A VFD converts 50 or 60 hertz power to a new frequency in two stages, the rectifier stage and the inverter stage. This conversion process incorporates three functions. The rectifier stage. A full wave, solid state rectifier converts three-phase 50-60 hertz power from a standard utility supply to either a fixed or adjustable DC voltage. The inverter stage. It's electronic switches or power transistors switch the rectified DC on and off and produce a current or voltage waveform as the desired new frequency. We have the control system. This electronic circuit receives feedback information from the driven motor and adjusts the output voltage and frequency to the selected values. Usually the output voltage is regulated to produce a constant ratio of voltage to frequency, or volts per hertz. Controllers may incorporate many complex control functions. The output frequency and voltage is adjusted by varying the duration of each IGBT pulse. This is where the term pulse width modulation comes from. And finally, the microprocessor interprets user commands through a keypad, input-output terminals, or communication protocols, and regulates the modulation of the IGBTs. During acceleration, the inverter applies different frequencies to the motor. It also changes the voltage, but in direct proportion to the frequency. This is known as constant volts per hertz and provides constant torque while the motor accelerates. The inverter produces rated motor torque from 0 to rated speed. it will produce full load torque while drawing much less than full load current from the power line during starting. This is due to the fact that the motor is effectively always running at speed for the applied frequency. Components of the VFD system. We have the inverter duty motors and why you should use them. There's voltage spikes. VFDs generate voltage spikes, and inverter duty motors are wound with inverter grade magnet wire, which has a higher resistance to voltage spikes. The wound motor poles are then dipped in a premium varnish and baked repeatedly. The varnish is built up to a higher thickness than a standard motor, adding to the increased ability to withstand voltage spikes. Overheating. Inverters allow standard electric motors to be fed at simulated low frequencies, letting the motor turn at low speeds. This means the shaft-mounted cooling fan of the motor is also turning at low speeds and not delivering enough cooling air. Inverter duty motors either rated to operate at higher temperatures or have a constant speed auxiliary fan which provides cooling at low speeds. The variable frequency drive. It generates the power to be transmitted to the inverter duty motor. Line reactors. A line reactor can protect motors and reduce power line distortions from VFDs. A line reactor acts not only as a current limiting device, but it also filters the waveform and attenuates electrical noise and transients associated with the system. You can install reactors in mixers, rotary dough feeders, sandwich machines, and many other types of equipment to extend the service life of the VFD and motor. The installation of load reactors with drives and motors can reduce the high frequency currents in motor and protect the motor from long lead effects. Basically, the reactor attempts to recreate a sine wave, thus improving overall system performance, reliability, and efficiency. It may reduce audible noise by as much as 5 dB. Tests have shown motor temperatures can drop by as much as 20 degrees Celsius when using a harmonic compensated 5% impedance load reactor. On the line side, reactors stabilize the current waveform with reduced harmonic distortion and the burden on upstream electrical equipment by absorbing line spikes and filling some sags that can prevent overvoltage and undervoltage tripping problems. For example, when the utility switches power factor correction capacitors on the electrical power grid, it creates voltage spikes. The impedance of the reactor in the input circuit helps prevent these voltage spikes and virtually eliminates nuanced tripping of drives due to overvoltage. A line reactor can also filter out pulsed and notched distortion, which can minimize interference with other electronic equipment like computers, PLCs, telecommunication systems, instrumentation, and other VFDs. The use of a line and load reactors increases the reliability, performance, and efficiency of a VFD system. It extends the life of both drives and motors and reduces the amount of energy consumed by the motor/drive system. Energy savings. Rising energy prices create a need for energy-efficient motor control solutions. To help reduce energy losses, process engineers are turning to VFDs as an alternative to fixed-speed controllers and throttling devices such as dampers and valves. Advancements in drive technology, careful selection of the hardware and power systems configurations, and intelligent motor control strategies produce improved operating performance and control capability and energy savings. Things to consider when choosing a motor control solution include peak demand charges, operating at optimized efficiency, power factor, isolation transformers, cost and losses, regeneration capabilities, synchronous transfer options, and specialized intelligent motor control energy savings features. Beat peak demand charges. VFDs also affect peak demand electricity prices that the utility charges to companies that exceed preset limits, such as when industrial motors are started across the line, they draw large peaks of current. VFDs help reduce these peaks by supplying the power needed by specific application and gradually ramping the motor up to speed to reduce the current draw. Power optimization. Centrifugal loads offer the greatest potential for energy savings by using variable frequency drives to control speed. Energy consumptions in centrifugal fan and pump applications follows the affinity laws, which means that flow is proportional to speed, pressure is proportional to the square of speed, and horsepower is proportional to the cube of speed. That means if an application only needs 80% flow, the fan or pump will run at 80% of rated speed and only require 50% of the rated power. In other words, reducing speed by 20% requires only 50% of the power. Power factors makes a difference. Power factor and how it affects displacement and harmonic distortion is another important consideration in drive selection. Drives that are near unity true power factor translate to reduced energy use. Use one drive for multiple motors. Synchronous transfer capabilities uses one VFD to start multiple motors to reduce full load current and reduce energy consumption. Programmability. Users can program their VFDs to adjust the total acceleration time and current limit and adjust the speed to the load requirement. Current limit on drives is normally set between 105 and 110%, whereas the cross-the-line starting method produces current limits of approximately 650%. Generate your own energy. Some VFD applications enable users not only to save energy, but to regenerate power, which can be routed back to the system or sold to the utility for additional revenue. Regeneration. An AC motor may act either as a motor that turns electrical power into mechanical power or as a generator that converts mechanical power into electricity. It depends on whether the motor is turning a machine that requires power to turn the machine or whether the load of the machine will at times overhaul the motor. Overhauling is a condition where the mechanics or the physics of the load mechanically calls the motor to attempt to turn faster than the motor speed the drive is commanding, and the drive is used to slow down the motor speed. This overhauling condition may exist in several types of applications. Constant deceleration. When a load such as a decline conveyor operating under the influence of gravity will overhaul the motor speed, and the drive is used to control the conveyor speed to a slower level than what the natural physics of the application would produce. Periodic deceleration. When a load is stopped quickly, an inertia of the load wants to keep turning, such as a large drum. In this case, the cycle time, or how many times a load is stopped over time, as well as the magnitude of the stopping power required, determines how much energy can be saved. System tensions and holding torque. When two sections of a machine are used to create tension on a material between them, such as on a metal strip or in a strip mill, the two sections may be running at the same speed, but the process requires a certain amount of tension on the strip to run properly. This means the lead section will run forward direction and pull the strip, and the following section will also run forward direction at the same time provide the needed torque in the reverse direction of the strip, thus creating the proper tension. In each of these examples, the motor and drive combination has the ability to recover the electrical power produced by the motor when it is acting as a generator, and send that power to the utility company. How much energy is saved is dependent on the application, but it can be significant. One such application where significant savings can be recovered is a gearbox test stand. When the gearbox is tested, one drive and a motor are used to turn the gearbox, while another drive and motor are used on the other end of the gearbox to simulate the load. Done correctly, this application will operate with a very low amount of total energy, as the amount of energy used to turn the gearbox is the same amount of energy that is recovered from the simulated load on the gearbox, less the losses in the system. The one question you should ask when trying to determine if the application is regenerative is, does the load at any time try to turn the motor, or is the motor being turned by the load? A common bus. When there are multiple AC drives in one location, a common bus system is usually the most efficient way to operate. It can incorporate the energy savings and recovery concepts that I have just discussed, If there is a regenerative AC drive and motor section in the system, it is ideally suited for maximizing energy recovery and cost savings. Mixers using VFDs. The VFD option provides several advantages over the conventional two-speed mixer that have the potential to improve product consistency and operational efficiencies. The ability to select mixing speed at will means the mixing profile can be developed to match the characteristics of each type of dough. This is a level of control not available on mixers with two-speed motors. The single-speed VFD motor is also less expensive than the two-speed alternative. Profiles can be developed that base the mix cycle on energy input, final mixing torque, and time, or a combination of all three. This can give higher levels of consistency and can also significantly reduce energy cost. Adjusting the speed of a mixer during the mix cycle may also allow you to decrease the mix time while still introducing the same amount of energy into the mix. The variable frequency drive provides improved working conditions with less noise and vibration as the machine starts up and changes speed. This also impacts on the maintenance requirements. A further benefit in the elimination of the power surge that can occur on a two-speed mixer is started or changed speeds. This can cause a drop in factory voltage and reduce torque on the mixer motor that may lead to stalling. Advantages of the VFD. Mechanical stress. The wear and tear of constantly hard starting a mixer at full speed can significantly reduce expected life of the machine. Conversely, when a VFD performs a soft start, it simply starts the machine at lower speeds and ramps it up over time. These soft starts and stops can significantly increase the life of your equipment. Safe off. This prevents the drive from delivering rotational energy to the motor. We are able to create a machine that complies with today's safety standards and keep the operator and maintenance personnel safe at all times. This device ensures the VFD will not fail in the on state like a standard motor starter can. Less noise. Two-speed mixers generate loud sounds and startups and speed changes. A VFD can eliminate this. Controlled stops. Machines can be ramped to a stop with the activation of an emergency stop. Machines equipped with starters may require long times to come to a complete stop. The cost. A VFD system today costs less than a two-speed system. Most of the savings would come from the cost of the motor. Reduced energy consumption. Eliminate the high inrush of current to the starter or the motor by ramping it up to speed. Recover wasted energy by putting it back on the grid. Flexibility. You can change speed, torque, and current settings to the motor. Torque. Relatively high starting torque. With a VFD, the motor runs virtually at speed during acceleration. Since the voltage is reduced at low speeds, the input current can be 10% or less with more than 150% torque available. Disadvantages of the VFD system. The system footprint. The electrical enclosure will be larger than a system using a two-speed starter of equal horsepower. This can be an issue as some bakeries do not have the available space for a bigger control enclosure. Heat. VFDs generate heat. This heat needs to be removed from the electrical enclosure to ensure the operation of the VFD. This can also reduce the life of the system and other control components. Due to the environment of a bakery, you may need to use an air conditioner to cool the enclosure. Complexity. VFDs require programming and will need qualified personnel to work on the system. Troubleshooting can be very difficult due to the number of components involved. Advantages of a motor starter. They're simple. There's no complicated electronic circuits. Easy to replace broken parts. The size. Control enclosure will be smaller than a system running on a VFD of equal horsepower. In some bakeries, space can be hard to come by. Temperature. This system is simple and does not include any transistors that may be affected to generate heat. Cooling will not be required for the system to remain operational, and no software to program will be needed. Disadvantages of a motor starter. The cost. Two-speed motors cost more than single-speed inverter duty motors cost. They're not flexible, no ability to fine-tune the process. The higher inrush of current. When full voltage starting, the slip of the motor at zero speed is 100%, and the motor is highly inductive. This results in very high inrush current, 600 to 800%. Torque. Relatively low starting torque, 150 to 180% of full load torque, compared to the current draw. Almost all motor current here is reactive, and reactive current by nature does not produce torque. When a motor runs at speed, the slip is typically in the area of 1 to 3%. Under this condition, the reactive current is much less than the motor produces rated torque at rated current. With a VFD, the motor runs virtually at speed during acceleration. Since the voltage is reduced at low speeds, the input current can be 10% or less with more than 150% torque. Mechanical stress. The short acceleration time of the motor generates undue stress and shortens the life of the mechanical system being driven by the motor. Deceleration. No ability to decelerate the system with a starter. This could lead to issues related to safety guidelines. The failure mode. In the event the contacts weld shut, you lose the ability to shut off the motor. The motor may continue to run even after an emergency stop has been activated. This concludes the prepared part of my presentation. Now I will open the webinar to discuss your questions and comments.
The conference is now in talk mode.
Thank you, John. We open up the lines for any questions. Any questions? No? All right, well, thank you for joining us today for the Peerless Ask the Expert webinar series. Please plan to join us on May 9th, 2013 at 2 p.m. Eastern Time for a review of the importance of preventive maintenance schedules with two of our senior service technicians, Mr. Patrick Smith and Mr. Gus Milliker. Until then, this is Melinda Cerigio. Have a great afternoon.